Okay. Hello, everyone. Welcome to another SciML seminar. We've got Nausheen Basha from the University of Manchester here to talk about using machine learning to aid fluid dynamics-driven engineering design. But anything else, I'll hand it over to you. Thank you very much.
Thanks, Miranda. Right. The title of my talk is a bit mouthful. It's an amalgamation of a few things. So it has the optimization element, and then it has a surrogate modeling element, and all of it applied to fluid dynamics-driven engineering design. And I'm based in chemical engineering department, so all of these methodologies are applied to chemical engineering. To get an idea of where my research stands, so it is at the intersectionality of few things, which is machine learning, computational fluid dynamics, and design, and for chemical engineering. Okay, the core idea of the research that I do is design influences performance, and that's valid for various domains, from aerospace to biomedical to chemical engineering. In aerospace, more commonly, if you have an airfoil, you can put a control points around that airfoil, which then changes the shape of that airfoil. And then you can get a gradients associated with the drag coefficient, and then you can play with it. And finally, you end up with an interesting looking shape that would optimize for your performance that you're looking for. In this case, it is a drag, which delays the separation point, improves the drag, then you get a very interesting airfoil. It's also been done in biomedical, though it's a very simplified version of a kidney exit problem. So what you want is a kidney stone not to be stuck in these vortices. So you want a faster washout of kidneys. So how would you change a certain geometries in order to achieve a faster washout? In this case, which is a mixing problem in chemical engineering, which is very commonly seen. So how do you shape optimize for these two cylinder sort of features that are rotating in a cylindrical domain in order to achieve certain level of mixing within a given time horizon? So in all of these examples, design has quite a good influence on performance. So that leads to the content of my talk. In the first part, how can we optimize for design? What would be efficient computational methods in order to explore the design space, where we look into something called as multi-fidelity Bayesian optimization methods. In the second part, where in the first case, when the geometry and performance is learnable, but the bottleneck there is a manual parameterization. In the second part, how we can jump up from the manual parameterization, and can we learn geometry representation itself from a certain set of images and do an optimization over that, which then helps us to explore large dimensional data set. And the third part of the problem, where in first two cases, we always have a fluid dynamics model or physics-based model in the optimization loop. So can we have some surrogate-based models, which are for really complex geometry conditioned two-phase flows? I think Julius Rumlu is on the call, so he actively works on the third part of this problem, on developing surrogate models for complex two-phase flows that lead to quicker inference. Or about plug flows. This work has been done in collaboration with very brilliant people, Tom Savage, Antonio, Jonathan McDonough, who's an academic at Newcastle, and Omar Matar, who is a professor at Imperial. Right, so plug flow is where when you have enhanced radial mixing and reduced axial mixing, right? So anyone who does fluid dynamics, you know that when you have a flow through a pipe, you see this kind of a lump profile. But then with plug flow, what you have is a profile that looks like this with of course, there is a slip at the wall, but majorly the profile looks like this because of how there is a flow that is being developed in these kind of cases. So this kind of a plug flow where you have increased radial mixing and reduced axial mixing, it occurs at higher Reynolds number. So we go back to the paper that was published by William Dean, and that was published in 1928, 98 years ago on the Dean vortices occurring at Reynolds number, specific higher Reynolds number in the coiled tubes. So William Dean was a professor in the maths department, and this is the paper that says if you have a fluid motion through a curved channel, there is a formation of Dean vortices at a higher Reynolds numbers. So and that has been studied also through various literature in chemical engineering, where it says that you can only achieve plug flow kind of performances and Dean vortices at higher Reynolds number. So what we are interested to find out, can we achieve this phenomena at low Reynolds number, as low as Reynolds number 50? Because the Dean number itself, it depends on the Reynolds number, of course. And if the Reynolds number is reduced, what we are left with is the geometrical parameters. We are left with the diameter, radius of curvature. So can we play with the coiled tube shape in order to achieve Dean vortices at lower Reynolds number? So what would be our strategy to do? That is the question that I'm trying to look into the next few slides. And also here I want to show how Dean vortices has been really useful in nature and how nature has exploited the Dean vortices phenomena. For example, in an iota, so you'd see there's a pulsating flow that comes because of the pumping of the heart. And then you have a mixing associated with the Dean vortices in an iota, which has been observed. So the Dean vortices, either it can occur at high Reynolds number, or when it occurs at low Reynolds number, you need some kind of an oscillating parameter. So you need an oscillating Reynolds number in order to achieve Dean vortices. But what we here want to find out again is we don't want any oscillating phenomena. We just want low Reynolds number. Can we shape the reactors in such a way we can still see Dean vortices? And an example of it is in venom generating cobra. So they have this, the orifice or the tracts, where which leads to the formation of Dean vortices, and that reduces the pressure drop, and it's useful to inject venom for the cobra to target and inject that venom. And here, Dean vortices are also used in lots of fertilization studies in order to segregate good sperms from embryos. So that sorting mechanism is also driven by Dean vortices. So it has been explored quite a lot in nature and how to manufacture Dean vortices artificially. But since I work in chemical engineering, Dean vortices are quite useful for manufacturing of pharmaceutical products, like crystallization for ibuprofen or paracetamol, or also manufacturing of vaccines, because you want two components to mixed in an efficient manner. And if you have really high Reynolds number, that could lead to degradation of some of the biological compounds. Okay, so what are the challenges in exploring this design space? So some of the challenges are the computational models are quite expensive, like fluid dynamics is quite expensive. So how do we go about looking through a huge parameter space? And these design spaces are high dimensional in nature. There are numerous design evaluations that you'd be expected to do. And also sometimes the gradient information may or may not be available. In order to explore it in an efficient manner, we look into the idea of fidelities, and it is underpinned by phenomena by George Box, who has this philosophy that all models are wrong, but some are useful. So we will see how we can explore this kind of a philosophy. Okay. So imagine if you want to draw a cat or identify a cat, right? So even with a very simple image like this, which is a child's drawing on the left, you can say that it is a cat. You do not need a really artistic, photorealistic artistic venture to see that it is a cat. Which is on the right. So the idea is that what is the least amount of fidelities? How can we have fidelities in a computational model that we can get away with? And what would it mean for something as designing a reactor? So this brings me into this kind of a chart where you have an accuracy on one side, there is a cost there. So the more you're increasing for the accuracy, the more it tends to get expensive. So, for example, if you want to design a reactor, even there is a complete guess, then there are a mechanistic model, there is a CFD simulation, then the pilot scale or a lab scale of how reactor would work. And then there is an actual reactor in an intended setting that's used for manufacturing. So you can put this in terms of an increasing accuracy. And we are dealing somewhere here with a computational fluid dynamics model. And within the CFD model, you have starting from coarse mesh to finer mesh. So anyone who does fluid dynamics or any physics-based model would know that if you have a higher grid density, then it becomes computationally expensive, right? So we explore this particular aspect of fidelities into our model. How can we explore through lots of low fidelities and few expensive fidelity, which is like a finer mesh, and then we can still arrive at an optimal solution in a computationally efficient manner. So that's how we explore this kind of problem rather than exploring through a fine fidelity throughout, which makes the problem really expensive. Now, if you see this chart on the left, what you will see is there are multiple fidelities. So you have starting from Z1, sorry, on the right, Z1 to Z5, and n is the objective function. So in the next few slides, I'll tell you what n really means. But for now, n is an objective function. So what you see here is that Z1 is the lowest fidelity, and this flat line is an experimental data. So when you have the lowest fidelity, it's far away from the experimental data. When you're increasing the fidelities, then it gets closer to the experimental data. So therefore, this is Z1 is faster, and probably Z5 is like really expensive. So now we want to explore it through this kind of a parameter space within your optimizer. Okay, I'll briefly talk a bit about Bayesian optimization before I talk about how do we include multi-fidelities in Bayesian optimization. So if you have certain set of points, maybe they are experimental or computational points, you get a fitting function around it. That's like acts like a surrogate model. So here you have Gaussian process. So when you do kind of fitting, you get a certain uncertainty distribution around it. Here, what you have is an epistemic uncertainty. If you have more data points, then the uncertainty of this would reduce. And what typically you have in Bayesian optimization is it's an acquisition function. So there is an exploration versus exploitation. So basically, where do you want the next point to be? So therefore, where you have a maximum or a minimum objective function, depending on what you want. If you have your x, which is an input design space, and then f of x is a function that you want to optimize for. So what would be the parameter like xn of 1 or xc of 1, where you want to put the point, which would maximize for this kind of a function. And you evaluate that through a black box. Though CFD itself is not a black box for human beings, but for an optimizer, treats it as like a black box. So therefore, those function evaluations are done in a CFD model. So based on the domain that you're looking into, you could have all kinds of varieties of Bayesian optimization. So here, this is just few limits that I have, a few examples that I have shown. So there could be, instead of going through a serial sequencing, you can do a parallel Bayesian optimization. You can have 5 explode together, then you have other 5, and then you can do it more in a parallelized manner. And then you could have multiple objectives. So in my problem, I'm only looking into a single objective, which is to maximize for plug flow performance. And then, of course, the problem that I'm interested more is looking through multiple fidelities. this is a bit that I spoke about in terms of exploration versus exploitation. So when you have an acquisition function, there is a classic tension between how much do you want to explore and how much do you want to exploit. So exploration is where if you want to have a point where uncertainty associated with the objective function is higher, you're more tending towards exploration. If you are putting a point where objective function is expected to be higher, then you're looking more into the exploitation space. And then if you have X, which are your input parameters, and then Z, if you have your expense or your fidelity, they could be independent or they could be dependent. So if they are independent, that's easy because you can then do a bit more sequentially. But if they are dependent, then it's better to do them simultaneously. So if they are independent, you can select X first. And then after selecting X, you can then select the cost, which is Z. So this is how the mapping would look like. And then if you have something that is dependent, then the mapping would look like this. And then you have to select both Z and X simultaneously, and you'd have to trade off the information and cost probably in a single step. So in our case, it's more of a dependent case. So we have to now do it simultaneously. So one objective function is the plug flow, and the second objective function is the cost. So what we now have is two different Gaussian processes. So with X as input parameter and Z as fidelity, and how we weigh them. We have based some of the strategies of this work based on this paper from Theodorf, which looks into ice sheet simulation. So here what we do is there is an information gain versus the cost. So we trade off the information gain with the cost through this cost-adjusted acquisition function. And you will see the results of this sooner. Before that, I'll show you how the workflow looks like, because as we go through the workflow, we will try and develop a surrogate model for CFD, not for exactly this problem, typically for other problem. So when you start this, you have certain input parameters, then you put those parameters through a CFD model, you get the plug flow, and then using those input parameters and the plug flow, you develop a Gaussian process, which is a surrogate. And then what you do is then it will give you, based on acquisition function, what's the next parameter you want to evaluate for. So that parameter goes onto the CFD model, added to the data set. And this sort of a process continues until you have some kind of a convergence criteria or a stopping criteria. And that is based on however you want to do it. There's no right way to do that. If you think that your computational cost is going to be so expensive, then you have to stop at maybe 20 or 30 iterations. That's okay. But that depends on your own criteria in terms of how to stop it. So this is done through an automated loop with OpenFOAM and PyFOAM library. And some of the Gaussian process functions are considered through GPJAX library. Here, I would like to show you the computational model. What does the plug flow mean, and how do we get the plug flow? So I say about that we want to optimize for the shape of the reactor. The idea is that if we optimize for the shape, then we can 3D print it. So it is feasible to achieve. Okay, so you can realize the designs through 3D printing. So that's why we're keen on optimizing for the shape. It can be 3D printed, and those designs can be achieved and also be validated. In any case, so if you have a coiled reactor that looks like this, the reactor is then meshed. It's put through a fluid dynamics model. So here is an physical experimental rig. So you inject the tracer for a few seconds, then wait for the tracer to exit the reactor. Then you can have at the outlet you have a concentration with time. You plot for the concentration with time with a plot that looks like this. And there are certain ways to non-dimensionalize this because you have different shapes. So therefore, it's easier to non-dimensionalize, so it becomes comparable. And what then you do is that there is a single equation model in chemical engineering, which is called as like a tangent series model. So you fit it with the model, and then you get a one single value of n, which is a plug flow performance. So higher the value of n, for example, in this case, the n value is higher, so therefore you see a nice narrow curve. And in this case, the n value is poor because therefore you see a broader curve. And because this is considered axial, you can imagine that the mixing is more concentrated here, and then mixing is poor on this side. So here you can imagine this as like a plug flow performance where most of the mixing is concentrated like this. So what you ideally want is a very narrow distribution of n or plug flow performance. And you see that through a parameter, which is like n. So in terms of fluid dynamics, we solve for Navier-Stokes equation, and along with that, we solve for advection diffusion equation to track the concentration in the medium. Okay, now looking through the results on how we first parameterize the coil. Now you can take this coil, okay, vanilla coil geometry, and you can dissect that into various cross sections. So each of the cross sections now is like a circle like this, and then your optimization parameter is the radius from the center point to the black point here. And then you have you have multiple radiuses. So you have 6 points for one particular cross section. So you have multiple radiuses. So you have 6 radius for cross section, and then you have 6 cross sections. So therefore, 6 into 6 is 36 parameters that you're optimizing for. Since you want something much more smoother, you don't want sharp edges because you're looking into more coiled kind of a surface. So what I have done is here you have it's a Gaussian process, a polar Gaussian process, which was done by one of the PhD students called Tom Savage. He cleverly applied polar Gaussian process, so the shape is much more rounded. You always tend to get rounded shapes. And then what you do is, since you have now you have various curves along the cross section of the coil, now you can merge all of them together into a manifold. So therefore, you end up with a interesting looking coil cross sections like these. And also you have certain axial coordinates, which are through polar coordinates. And therefore, you can get a few axial directions to the coil as well, which would lead to interesting shapes of the coil like this. So you have some radial parameters and axial parameters leading to clearly complex coil shapes. So then we put through these design parameters into a multi-fidelity optimizer. So if you look at this plot here, I'm not sure how visible it will be for online people, but if you look at the middle plot, right, you have an objective, and then you have an iteration on the x-axis. And then what you have is a simulation cost, right? You see a lot of blue peaks, and then you also see a few red peaks. From this case, what you see now is that Optimizer explores a lot of cheap simulation, which are blue peaks, and few expensive ones, which are red and orange, and it arrives at an optimal solution. And here, if you see at the simulation cost with respect to the wall clock time, so therefore something that's expensive would have like a wider profile for wall clock time. So you see a sharp, narrow peaks of lots of cheap simulations, and then few wider peaks that you see for the wall clock time. And then the point is that you can now get to an optimal solution by exploring lots of cheap simulations and then only a few expensive ones. So that makes it efficient in terms of time in order to get to an optimal solution. And then finally, we get to a shape that looks like this. And we visualize for that shape with fluid dynamics model. And then we finally see formation of Dean vortices. that you didn't see with a vanilla coil that is just simply coiled like this. So, which confirms that the Dean vortices are occurring, but now we want to see, can we validate it again with experiments so we can see a good plug flow performance. Therefore, what we do is that we increase the length of the coil. So this is the vanilla coil. And then you have another coil, which is on the rightmost, which is a shape optimized coil. The number of turns are repeated. And then what you see is that the improvement in performance by almost 60%, which confirms experimentally that there is a formation of Dean vortices through a good plug flow performance. So there is, if you're more interested about this work, there are lots of papers that are published on this work, starting from this work is more on the fluid dynamics aspect. Then you have some work more on the optimization models, and then a third work with fluid dynamics plus optimization plus experimental validation. So, so you can see the methods much more clearly. Okay, so in the next part of the work, right, in the previous work, we had lots of manual parameterizations. So those parameterizations are pretty much human intuited parameterization. But in real life, reactor shapes are quite complex. So they are not like 36 parameters. And then you're also, if you're using Bayesian optimization, you're also limited in terms of the dimensionality. You can't explore a huge design space. But the real world doesn't work like that. In real world, you have much more complex shape. For example, here we have a case of ShapeNet. And ShapeNet, if you just take a case of a lot of data set on flower vase, so you can see a lot of various looking flower vase features. So now we ask the question, can the model learn geometry representation? So probably if you give a model an image, can it learn some kind of a geometry representation from it in a reduced manner? And Bayesian optimization can work on that reduced representation or latent representation of that model. So can we construct something from the reactor shape? So this work is done by Marco and Tom, who were my undergraduate students when I was a postdoc research at Imperial. So this work is still an ongoing work, but what we did is we took certain images, but not the images of really complex shapes, because we wanted to test an idea that if you have an images like this, generated images like this, which are generally like sine curve and random Fourier sum, can you then put through, can you then get a continuous latent space, and can you work and optimize it over the latent space and still do an optimization for some kind of a realistic chemical engineering problem? So there were a lot of images that were generated for this purpose based on various kinds of sine curves, various kinds of random Fourier sum. So probably 2,000 images that were generated with certain levels of pixels. And we put that through variational autoencoder. So you get the data set, you encode it out, then you get a latent space, and then you decode it. Now, if I quickly show the training results, I'll get to the details in the next few slides. So what you can see is that it is a bit blurry, but it is still, you get a decent reconstruction from the latent space through the decoder. So here I want to show a bit on the amalgamation of various loss functions that were used in order to reconstruct it from the decoder. For example, there is a binary cross entropy loss, where if you have these as an input geometry, you reconstruct that as through BCE loss. What you now see is that they're very diffused. So you can see that some of the finer features are not well captured. It does capture the element of the wavy or the sinusoidal element, but there are so many finer features there that could not be captured. And these fine features are important for fluid dynamics. Later on, In the next case, you will see how small change in the feature can affect the characteristics drastically based on the fluid physics or fluid phenomena. But anyway, so it performs really poorly. Then we go on to a dice loss function. So it tends to get a bit more better. So you start to see some of the features emerging. So you can see how this feature has emerged. So there are some of the features that are emerging there. And therefore now if you reduce the threshold, and then you can see that it can reconstruct it in a decent manner. So it is a combination of few loss functions that led to how you can reconstruct this kind of an image. So I'm thankful to Marco to test various loss functions and get to these kinds of loss functions on reconstructing the geometry. Okay, now going to the optimization loop itself. So you have an initial data set that has various reactor shapes. Now you put through that encoder, and then you get a latent space, right? And then now you fit a Gaussian process in a latent space. It predicts for what would be the next set of parameters that needs to be evaluated for. And those parameters then go into the decoder. Decoder reconstructs the full reactor geometry. So you get to the reactor, you run fluid dynamic simulation for the reactor, and then you get a result from it, and then you go on to the Gaussian process. So this sort of a process continues. So now what's different that you're doing now is that you're now operating on a latent space, continuous latent space, and you're letting the optimizer work on the latent space. So now you can have really complex shapes. You can reduce down the dimensionality. You can let it operate on this kind of a dimensionality. Okay, so I want to show you a few results. So this is a case of manufacturing ibuprofen. So you have two different fluids mixed with each other. So there is a formation of crystals once the fluid would mix. So here, what you see here is that if you have a non-uniform distribution, the crystal size would be much more broader. If you have a good uniform distribution, the crystal size would be narrow. And typically what you want is the crystal size to be narrow, which is good for therapeutics, which is good for manufacturing, which is good for all sorts of downstream process. So a pharmaceutical industry would want the particle sizes to be in a narrow kind of a range, and that's influenced by mixing. And now if you look at the TSNA analysis and iterations, you will see that we start from this region, and then slowly we get to the region of where you'd have more optimized geometries. And if you compare that again with the objective function, so here you'd see a lot of poorly performing geometries, and gradually we get to the geometries that perform well. So the geometries that tend to perform well, you can see there is a curve at the beginning. There is a bend, or there is a curve at the beginning. So TSNA analysis is also a good way to map out geometries that are similar in feature in one kind of a map, so you can see what similarity in features leads to what kind of an objective function. So again, in this case, if you look at the concentration or the diameter of the particles, you would see that it's more uniformly mixed compared to something that's more vanilla, which is not uniformly mixed. Okay, so now I get to the third part of the work, which is primarily done by Julius, who's on the call. Here, in previous cases that we saw, we always had CFD optimization, CFD model in the loop. Now here we ask questions on how we can have a surrogate model, that too for a really complex two-phase flow case, and what are the challenges associated to do so. And this is quite important because in design problems, you have hundreds of forward evaluations, or they're so-called multi-query problems. right? So you have to evaluate through a lot of designs in order to come up with an optimal solutions. And when you evaluate through those designs, you have lots of CFD models that are being generated. So you can use those models probably to develop a surrogate model. And then one of the challenges that if you have like two-phase, which I will show in a minute, it gets hugely complex developing a surrogate model. Maybe for an airfoil, yes. Maybe for a cavity flow, yes. Probably when you have two-phase complex with an interacting boundaries, it gets quite complex. So the challenges in the case that we're looking into is like a highly non-linear interface. It is time varying, it is free boundary, there are adaptive discretisation, and you need to capture for finer scales. The finer scales are quite important in the problem that we are looking into. So the question is, can we learn compact surrogate representations for these more complex geometry condition transient flows? Here I want to show an example of how the geometry condition flows occur in nature as well. So for example, if you look at this example of cobra again, and then if you see the case where cobra is ejecting venom through forward-facing fang orifices, so a cobra would know how to regulate their orifices in order to achieve a certain kind of spray characteristics that they want for their venom. And then if you look at the archer fish, right? So archer fish would also know how to generate a kind of a water jet through their tongue palate groove. So they know how to play with the geometry of their fangs or geometry of their mouth in order to achieve certain jet characteristics that they can attack the target. So some of the organisms survive by having probably a biological latent code in their brains on how to reconfigure some of the jet or spray characteristics with the shape of their mouths, with the shape of their venom, and that's the way to survive. Because if the animals didn't have a biological latent code, like the archer fish doesn't get multiple chances to attack an insect, they would drain the energy, right? You can't have many more trials, they would just drain the energy. So they have to learn a biological latent code to target the insect in the first go. So in our case, we look into, can machine learning understand some of this geometry with fluid dynamic relationships? So here I'll show you a case of an orifice of a nozzle. So here you have an orifice or a nozzle, and then fluid dynamic characteristics similar to that of water are then injected in the gas medium. So as soon as it is injected in gas medium, it undergoes lots of instabilities. There are primary instabilities, there are secondary instabilities leading to formation of ligaments, and those ligaments then break up and try to form droplets. So, and the nozzle, in the next cases, I'll show how the shape of the nozzle is changing upstream. Right. This is done in a solver called as Basilisk. So what you have here is adaptive mesh. Adaptive mesh here it's called like Optimisation grid refinement, which is useful to capture the filaments and the droplets associated with those. Imagine if you didn't have this adaptive mesh and you just have to mesh the whole geometry, it would be like super expensive. So it has this adaptive mesh feature to capture for these instabilities and capture the finer features. Okay, here I want to show if you have a different shapes of the nozzle upstream, you will see whole different fluid discretization pattern. So the change of the nozzle is not too much. There is only a very small change in the shape of the nozzle, but the spray pattern that you would see is drastically different. Like if you have this kind of a shape, it's more upstream. If you have this one, it would be more towards the downward direction. So the shape that you have affects, even if there's a small change in shape, it would affect the fluid flow characteristics, especially in a case where you have two-phase flows with blocks of interfacial instabilities. And if you now have to develop a model where you say, this is my nozzle, what would be the spray or jet characteristics from this kind of a nozzle? So we are now looking into a surrogate model to do so. Of course, there is a lot of literature in terms of surrogate models to do this. There could be neural operators, then there are autoencoders, there are some geometry aware surrogates, and so on. So if you have a neural operators where you're learning the mapping between the functions and the solution field, which is quite good. But however, you have the geometry variation there assumes kind of a fixed grids. So you don't have that kind of an adaptive mesh representation to build into the model. Then you have latent models like autoencoders. They are good in learning some of the reduced temporal dynamics. But however, if you have to think about a geometry variation, that could be much more complex. Then you have more geometry-aware surrogates like mesh graph nets, where you build the geometry through the mesh and the associated mesh coordinates within the geometry. But it struggles quite a lot with message passing. So we tried our problem with mesh GraphNet first, but it struggles quite a lot with message passing because a small change in geometry, the characteristics are affected much downstream. So the message passing layer really struggles to capture the length scale of the characteristics that are needed to capture this. So the point is that the various architectures, they look into one particular part of the problem, but a combination of the problems in terms of the geometry variation, in terms of the temporal characteristics of this problem, in terms of the adaptive mesh or the complexity, because solving two-phase flows without adaptive mesh is much more complex. So trying to build all together, that's been complex. So how do we pull various elements into the architecture to build something which is a joint geometry and flow representation that remains unexplored. So that's what we want to look into this kind of a problem. Okay, so we have for this, what we came up with is a two-stage process. In the stage one, we learn the solver's refinement structure or the adaptive meshes, which are like the physics-based proxy. And we use that physics-based proxy in order to get to the solution fields. If you have to learn from the coordinates of the nozzle to the adaptive mesh, that is much more complex machine learning problem. So what we do here, it's a bit more of an inverse kind of a problem where you have lots of adaptive meshes and you put that through an variational autoencoder. So you put that through a FNO and then you get a latent space and then you decode it back. Yeah, so if you scout through if you give me once you find the model, if you give a nozzle geometry, then it will scout through the latent space and then find out what would be the nearest nozzle shape that we have trained for, and then we could get a adaptive mesh through that, and we can put them through a stage 2, which is a unit, in order to get some of the solution fields. Okay, so let's see what kind of results we get. The results improve previously from various other models, but still the results aren't the best. We would again need to think about some of the additional architecture in order to do this. It's an ongoing work. Like you can see how it gets a bit more blurry. So if this is the ground truth and that's the prediction, it gets a bit more, you can see some of the major characteristics, but some of the finer details would be a bit more. Like for example, you can see some of the perturbations here, but you don't see a lot of perturbations, so it could get a bit more blurry. And therefore we saw that with the errors as well. If you have errors for volume fraction, velocity, view, as well as the adaptive meshes, then the errors tend to become greater with the time. So we need a bit more robust formulation in order to work with this model going forward. However, this has been recently presented by Julius, an AI for Physics conference. So this is a snapshot of the paper. Anyway, I think in the interest of time, I will now get to the conclusions part. where in the first case, we had a multi-fidelity Bayesian optimization, which helped us explore the geometry space in a more computationally efficient manner. But the limitation there was some of the parameters were human-intuitive parameters. It was a manual parameterization. So the next phase of the work also looks into how can we have some more clever way of parameterizing it. Can we have some images? Can we deduce some of the parameterization from those images? And then can we work with an optimizer? So that helps us explore combining this bit with the multi-fidelity based optimizations. Helps us explore much more interesting shapes. And then finally, we look into much more complex surrogate models developed for these kinds of problems where you have two-phase flows. Where in two-phase flows, there is, in most cases, there's an adaptive mesh, just because if you train it on like a really fine mesh of millions of cells, that would be a crazy amount of machine learning training. First, there would be challenges in generating the data. And then even if you have the data, it would be crazy amount of training. So how do we make it work on something as adaptive mesh, which are efficient way to generate the data and also do some of the training? And in future, how can we combine all of this into a workflow which is more comprehensive in order to explore really clever, really counterintuitive shapes? And yeah, thank you, and happy to answer any questions.
Any questions online, just put them in the box and I'll either read them out or then
I can start.
Yeah.
Thank you very much for this talk. Very much dense information to digest. But can we go to the fidelities when you were talking about?
Yeah.
So
Okay,
in
so-
the presentation.
Yeah. This one.
There's one, I think, right before where you were measuring, for example, when we have this architecture, what would be compared to the experimental results? Like we made. I think it's just.
This
Yeah,
one?
this
Yeah, yeah.
So I was just like, here what you are doing, like for the same shape,
Yeah.
you are getting more points to compute and then see what's the experimental.
So I have the same shape. What I have is changes in mesh density.
Yeah, but like, I noticed that there's a point above the experimental results, even though it has a lot of,
Yeah.
But doesn't like, this is, I'm not very experienced with, but like, it should be the same as the experimental one because.
Okay, so we have to remember that experiments have errors as well. So every experiment is generally plus or minus 15%.
Okay.
So it's really hard to say how the exact match would be really. And also another phenomena with the CFD is that sometimes you could see a saturation as well. It is, I mean, if you keep on increasing the mesh, at some point to reach a saturation or mesh independence, so you can see a flat curve. So you have to operate somewhere here rather than with this bit where it is already saturated.
Okay. There's also about the choice of finish optimization. Is there a certain way why it just went into this optimization, or are there other methods?
One is because with Bayesian optimization, you have least amount of evaluations that are needed. Mm-hmm. So with you could go with probably other optimization methods, but probably adjoint. But here we do not have gradients for an adjoint optimization, or you could go with some other methods, but there would be like thousands of evaluations with other methods. So one way to big Bayesian optimizations because of this. But of course, there's a challenges associated with the high dimensionality. With other methods, probably we call high dimensionality. But with Bayesian optimization, you can't do that. But since fluid dynamics is expensive to evaluate, so therefore we start with Bayesian optimization.
Well, that's right.
Yeah.
When you were looking, we're trying, okay, so we started here, the parameters were manually derived. And then the next thing that you did is that you get real architectures and you're trying to get these manual parameters for them. Mm-hmm. Right? So you started, let's say, with 20 parameters that you manually created, and then you did a machine learning model to try to see real world geometries and what's this amount of manual parameters are there.
Yeah, machine learning extracted parameters. That was the idea. That was the next study is like a bit of like a proof of concept. And it's not, I mean, that study is still, that's an ongoing study. It's a proof of concept on can we use machine learning to extract parameters to play with. If there are really complex shape, for every time to come up with a way to parameterize that complex shape could be, it could be expensive on human minds to do that.
Yeah, because I was wondering also that you started with a predefined set that you created.
Yeah.
What if, for example, this set is built has some missing parameters, for example? What if we want 100 parameters per geometry? I think this is
Yeah, there's always a choice that when you make when you do an optimization, there's always a choice that you have to make on how much performance gain are you going to get versus how many parameters are you going to use into the model. If we could have 100 parameters or if we could have 200 parameters, right? But if that's not going to, if you think that's not going to improve your final results, not that much percentage, then you should be a bit more considerate about the computational time needed to explore.
Just going to read out a question in the chat for the sake of the recording. Ben says, thank you for the talk. In the first section, you're looking at the Dean vortex and using scalar transport equations of open foam. His understanding is that you can't fully resolve vortices itself. Were you using a Navier-Stokes solver to get the fluid flow and scalar transport to then get the chemical diffusion through the solved fluid?
Yes, exactly. Probably I was a bit fast in that when I explained it. Yeah, exactly. You're right. Yes.
And I have a question about your, I think it was the VAE, the loss functions that you were using. There were 3 different components, and I was just wondering if you could give me some intuition on which of those. There's the KL divergence, I think. Yeah, those.
Yeah, the last one. Yeah, it's a bit funny on how this was done. I think the DICE has been used quite a lot in medical imaging as well, because you have that medical imaging, lots of data sets, and DICE has been DICE seems good. And then BCE has been used in, I think, various other cases. So we thought that one of it should work, and then probably it was seen that if we combine them, and that seemed to work better.
Can you give intuition as to like what each part of the loss is doing? Like, what does the DICE do?
Yeah, I think DICE is good in terms of continuous. So if you have something which is a bit more, you need a continuous representation of it. So therefore, DICE is good in regularizing that. And this is the most simple one. So in order to capture some of the, but it can capture a lot of discrete elements.
And then a follow-up question, not for that, but for the mesh discretite, your adaptive mesh does those 4 subgrids.
Yeah.
Did you look into other meshes, like triangular meshes, or is this just the?
Okay, with this case of 2-phase flows, it's quite complex. So you could have triangular meshes, but the solver will suffer from quite a lot of numerical instability. So even with the adaptive mesh that you're looking for, right? So it is like on the order of 8. On the order of 8, in the sense you start with a big block, you do like this, you cut them in a horizontal and vertical. So that is 1. Then you take 1 box and then you cut it again, that's 2. So it isn't on the order of 8. So you don't see a lot of meshes here. They're like tiny dots because they are not zoomed in. But for the numerical solver to be stable for this kind of a problem, so you would need even if I had it 4, probably it would be a problem, let alone triangular meshes, it would lose a lot of flux.
Thank you.
Okay. I had a couple of questions. So, you know, where you introduced the exploration versus exploitation expression, and you had a linear combination of the expected what do you call it? Expected loss, and then the variance of the loss, and you were trading these 2 things off. Why was it when you introduced the computational cost? Why is that? Is there an intuitive reason why it's in a reciprocal term, rather than being another additive term in that?
Probably of that.
Yes, and this one.
Yeah.
So what is which term is the computational cost?
Oh, so let me go to the. So this is the information gained, and this is the computational cost. So it is divided by the computational cost.
Oh, so
Okay.
you're finding a maximum.
Yeah.
So that you're maximizing the rate then.
Yeah.
Okay. And then my second question was, I don't know whether this occurs with fluids, but I was thinking in like a robotics context,
Yeah.
when you have your physical parameters, if they're your geometry parameters that are human created, especially if they're in polar coordinates, I imagine you could have sort of singularities in your space
Mhm.
where a very small change could produce an explosive change in your output.
Mhm.
Does that kind of thing occur in reactor design, or is everything quite smooth?
I mean, what you're trying to say is that if there's a small change in input, there's a huge change in the output characteristic, is what you're trying to say. Oh.
Yeah, so if your theta space, if it was in polar spherical coordinates, say,
Yeah.
at the poles you'd have singularities.
Yeah.
If you're using Gaussian processes, you're kind of assuming everything is a smooth function.
Mhm.
Is that a reasonable assumption of this kind of application?
It could be a reasonable assumption in this case as well, but yeah, it's just that I mean, it's not being explored in that particular way, but yeah, it's really odd.
Okay. Do we have any more questions from the room? Online? You thank the speaker again. Thank you very much for coming.
Sharing.